Hi everyone, today we're going to talk about section 5.7, which is the Pythagorean theorem, and a whole bunch of other things associated with the Pythagorean theorem. We're going to talk about the converse of the Pythagorean theorem, some application problems dealing with the Pythagorean theorems, and also some very early proofs of the Pythagorean theorem. So let's first start off with, what does the Pythagorean theorem state? Put the video on pause and write down your answer. So I hope you're back now, and so I hope you said that a squared plus b squared equals c squared. If you did, you were wrong, because that's not what the Pythagorean theorem states. It says that in a right triangle, the sum of the squares of the legs is equal to the hypotenuse squared. I am certain that Pythagoras, who lived somewhere around 569 to 500 BC, did not walk around saying a squared plus b squared equals c squared. That's a formula that we use to help us implement the Pythagorean theorem. So what I'd like you to do now is I'd like you to take a look at these next two problems. Put the video on pause, solve those, and come on back when you're ready. So for the first problem here, the equation that I have is 2 squared plus 6 squared equals x squared, and x is going to equal 2 root 10. For the next problem, it's a little bit more involved. I have the quantity of x minus 2 squared plus 4 squared equals x squared. I had to FOIL this out, simplify, and I get x equals 5. The next problem is an application problem. So I want you to put the video on pause, read this, come up with an equation, and solve it. Come on back when you're ready. So let's see how you made out. I ended up with the equation of x squared plus 3x squared equals 12 squared, and my x represents the width. How wide should the frame be? That's the question that we're looking to answer. And so I end up with x is approximately 3.8. That's my width. Okay. The next thing we're going to talk about are Pythagorean triples. Maybe some of you have already heard about Pythagorean triples. But if all three of the side lengths are whole numbers, if a, b, and c are whole numbers, non-zero whole numbers, then it's referred to as a Pythagorean triple. And it can be really handy to know these. I'm talking now in Stag 10, in pre-calculus, in calculus, to recognize Pythagorean triples. So the most common Pythagorean triples are the side lengths of 3, 4, 5. But from here, I can take each of these and multiply each side by any number, whole number, and create another Pythagorean triple. So if I multiply each side by 2, I get 6, 8, 10. That's another Pythagorean triple. I can multiply each of these sides by 3 and get 9, 12, 15. I can multiply each side by 10 and get 30, 40, 50. And I could keep going on and on and on. The next set of Pythagorean triples is 5, 12, 13. So again, I could do the same thing and multiply each of the sides by 2, each of the sides by 5, each of the sides by 10, and get another set of Pythagorean triples. The next set is 8, 15, 17. Another one is 7, 24, 25, and there are many more. Another common one that you will see quite often is 9, 40, 41. So now, why is it handy to know about Pythagorean triples? Well, if I gave you, for example, the side measurements of 15 and 36 and asked you to find the third side. If I look at 15, what the combination of factors that give you 15? 3 times 5. Whoops, 3 times 5. And then how about 36? That's 3 times 12. Well, if you notice, 5 and 12 are part of the common Pythagorean triples of 5, 12, 13. So if this side is multiplied by 3, this side is multiplied by 3, then this side is going to be, again, 5, 12, 13, and then I multiply it by 3, and I'm going to get my answer of 39. So it's a very quick way to solve for the unknown side, and your only justification that you would have to give me is to state Pythagorean triple. You don't even have to show me an equation. Just say Pythagorean triple. So for example, this one right here, if I said to you I have side lengths of 9 and 41, and this is unknown, then you could say 40 Pythagorean triple, and you're done. So what I'd like you to do now is there are 3 problems here where there are unknown lengths. I call this side x, this one y, and this one z. I'd like you to find the missing side length and determine whether or not each of these are Pythagorean triples. So come on back when you're ready. So for the first one, do you notice that this would be 2 times 7? This would be 2 times 24? And is there up here in my list 7, 24, 25? So if I multiply this by 2, my answer is 50. So this is a Pythagorean triple. For part B, again, this would be 3 times 12. This is 3 times 13. So here I have, again, 12, 13, go up here. So I'm going to multiply this side by 3, and my answer is 15. This is a Pythagorean triple. For this problem right here, I have 3 times 5, and this is going to be 4 times 5. So you might be thinking that this is going to be 5 times 5, 3, 4, 5 Pythagorean triple, but this isn't the longest side. So don't be fooled on this. This is not a Pythagorean triple. If you go ahead and solve this, this comes out to be 5 root 7. So this one is not a Pythagorean triple. The other thing too that you want to always check to make sure is that the measurements of the 3 lengths that I give you actually make a triangle. So that's another thing that you want to pay attention to, and that's going to come up in the next section when we talk about the converse of the Pythagorean theorem. The converse of the Pythagorean theorem, sorry about that, is saying that if the sum of the squares of the lengths of the 2 sides of a triangle is equal to the third side, then it's a right triangle. So again, we're switching up the given information. We don't know that this is a right angle. So if a squared plus b squared equals c squared, then this must be a right angle. Okay? So we can use this idea of the converse of the Pythagorean theorem and extend it to Pythagorean inequalities theorem to classify the remaining types of triangles, whether they're obtuse or acute. Okay? So if a squared plus b squared equals c squared, then we know it's a right triangle. If a squared plus b squared is greater than c squared, then it's an acute. If a squared plus b squared is less than c squared, then it is an obtuse triangle. Okay? So what I'm going to do right now is I'm just going to walk you through here. This one, I think is pretty clear that if I gave you 3 side lengths, let's say I gave you 24, 10, and 26. First of all, the C would always be the largest side measurement. So the question that you are going to ask yourself is 24 squared plus 10 squared, and I'm going to leave a blank to 26 squared. Basically, what you need to do is you need to fill in this blank with an equals to, greater than, or less than, and then you can use this to classify the type of triangle you have. So hopefully you already recognize this as a Pythagorean triple. So I could say that a squared plus b squared is going to equal c squared, so therefore it is a right triangle. But how about if I give you, let me see, the side lengths of 7, 8, and 10. So first of all, look at it. Does it make a right triangle? Yes or no? Does it make a triangle? Yes or no? And then you're going to use this inequality statement. So 7 squared plus 8 squared blank 10 squared, and fill that blank in. So take a moment, figure that out. So I'm going to get 49 plus 64 blank 100. And how are you going to fill that in? And the answer is going to be what? Greater than. So if it's greater than, then it's what kind of triangle? It's an acute triangle. And then the last example that I'll show you, if I give you 8, 15, 18. So 8 squared plus 15 squared, blank 18 squared. Do the math and figure it out, please. So hopefully you're going to get 289 is less than 324. So less than means that it's an obtuse triangle. So the way in which I get to remember these is I made up this little acronym, ERGALO. So if a squared plus b squared is equal to c squared, it's a right triangle. If a squared plus b squared is greater than c squared, it's an acute triangle. And if it's less than, it's an obtuse triangle. So that helps me remember the 3 relationships. Okay? So put the video on pause and again classify each of these triangles if possible, and make sure you show your work. And this is going to be really important for homework. You have to show or justify your answer. You can't just say, oh, it's an acute triangle. So hopefully you've come back and you've figured all these out. A is obtuse. B is not a triangle. C is acute. And D is a Pythagorean triple. Next thing that we're going to do is we're going to take a look at several proofs of the Pythagorean theorem. This is the Hindu proof. And all of the proofs that we have, the one including that you're going to do for our homework, which is the Garfield proof, based upon, which is the work of President Garfield. He used to be a professor. This first one is the Hindu proof. And basically, it's saying to us that, or the way in which we prove these, is that we prove that the area of the whole is equal to the area of the individual parts or pieces that are in here, in the interior. So ABDE is a square. All the triangles are right triangles. Therefore, all of the triangles are congruent by ASA. We have complementary angles, and angles 2 and 3 are congruent by congruent complements theorem. So to prove algebraically, again, these are algebraic proofs, that the area of the whole is equal to the sum of the area of the parts. So we're going to basically set up that equation. Okay? So give me a second. So the area of the whole, ABD, I should call it E, sorry, is equal to C squared. So again, the area of the whole is C times C, which would be C squared. And then we want to, or we know that is equal to the sum of the area of each of the triangles in the inner square. So these are the areas of those parts. So we end up with C squared is equal to 2AB plus A squared minus 2AB plus B squared. And when we simplify this, it comes out to be C squared is equal to A squared plus B squared. When we take a look at the next proof, which is called the Chinese proof, it's basically following the same format, is that we would show or prove that the area of the whole, which would be A plus B squared, is equal to the area of the inner parts, the 4 triangles in the inner square. So when we go to do that out algebraically, you should end up getting, so the area of the big squared is A plus B squared, which is this, simplified. And then the area of the inner parts would be the 4 triangles in the inner square, which was 4 times 1/2 AB times C squared. Simplifies to this. And so when I put them all together, I can simplify the example to a squared plus b squared equals c squared. So those are two proofs of the Pythagorean theorem. You'll do the Garfield proof as part of homework, along with some application problems. So hope you have some fun with it, and there's also some supplemental problems that you'll be doing as well. See you later.